We're in section 2.5, and in this section we're interested in working with derivative of trig functions. So here I have a list of trig functions that we look at. These are your basic trig functions, that is sine, cosine, tangent, and so on. We look at the inverse of these functions, the derivative of these, later on near the end of the course. But for now, just the basic trig functions. Now I've written this is a theorem actually in your book, and we'll prove one of them, and the rest of them you can prove the same way. Okay, so first, the function sine x, the derivative of sine, turns out to be cosine. If the function cosine, the derivative of cosine is negative sine. For tangent will be secant squared. Cotan is negative cosecant squared. And the derivative of cosecant is going to be negative cosecant cotan, and that for secant is going to be secant x tan x. Okay, so these are the basic derivatives. Now let's do a proof of cosine x. I believe sine x is in the book, but exercise number 47 actually in your textbook asks you to find the derivative of cosine. So let's do that. Now we can begin by the limit of the difference quotient. Remember, the very definition of derivative, the birthplace of that is from the difference quotient. So that's going to be cosine of x plus h minus cosine x. That would be like the rise, and h is the run here. And the limit gives you the slope of a tangent line. Now in the numerator we have this cosine x plus h. We can actually work this using the sum formula, addition and subtraction formula for cosine. So if you recall, cosine alpha plus beta is going to be cosine alpha cosine beta minus sine alpha sine beta. So doing that with this limit we're getting, so I'm just going to go now the notation cosine x prime, that means the derivative of cosine is going to be the limit as h approaches 0 of cos x cos h minus sine x sine h minus cosine x, and that divided by h. Okay, and let's see, so that's just applying the sum formula. We're going to split this into two limits now, right? So I'm going to from the first and the last term, they have cosine in common, so let's factor cos x, and that's going to give us cosine h minus 1 divided by h, and then minus, that's this minus here, and then minus sine x sine h divided by h, right? So we split that into two fractions actually. Now we're going to take the limit of individual items here, individual fractions. So the first one, and notice the variable of our limit. The limit is based on h. So with respect to h, we treat x as a constant, so cosine x could be brought out. And in fact, let's bring out negative cosine x. And we're going to multiply that by limit as h goes to 0. So I factored negative cosine h, which makes negative 1 a positive 1, and cosine h a negative cosine h divided by h. And in the second fraction, we're going to do the same thing. I'm going to bring sine x out and take the limit as h approaches 0 of sine h over h. Now both of these limits we worked earlier, I believe it was in section, whatever that was in chapter on limits. The limit of sine h over h approaches 1 as h goes to 0, and this first limit approaches 0. 0 times cosine x is of course 0, negative sine x multiplies by 1, so that's going to be negative sine x. And there you go, that is just the proof for that. Okay, So that's about all there is in this section. It's pretty brief section, not much, just the derivative of trig functions. Now, let's take a look at some exercises here. So for these exercises now, let's see, I'm gonna try and let me hold on. Okay, there you go. I just moved the exercises up a little bit here. Okay, let's take a look at exercise number 4. In all of these exercises, we want to find the derivative, except 26 and 28, they ask for the second derivative here. So we'll work our way to that one. So let's begin with exercise number 4. In exercise number 4, the expression is y equals square root of x times sine x. Now notice we have a mix of algebraic expression and trig expressions. Usually when that is the case, and you can see he's got a few of these, and later on we'll see more of this also. Usually with these, the final expression is not going to be like reducible, so they're not going to simplify that well, is what my point is. But anyway, let's go through the motions. Y prime. Now, each of these is in the form of a product, right, of the two functions I'm working with right now in number 4. So I'm going to let root x be like an f, sine of x would be g. So the structure of this function is in the form f times g. And again, the assumption is that all of these functions are differentiable over the domain, okay? Especially the trig ones, because in the case of like tangent, cotangent, secant, cosecant, we know there are vertical asymptotes, right? There are points where these functions aren't defined. So the derivative we assume exists over the parts that the function is defined, in fact, within the domain of those functions. So let's recall again the product rule of derivatives. F times g prime is going to be first time or derivative of first by second plus first times derivative of second. Okay, so for the product rule, this is what we're going to do. Now, derivative of square root of x, and if you recall, the square root of x is x to 1/2. So this will be easier to find the derivative of in the power form. Okay, so that derivative is going to be 1/2 x to negative 1/2. And of course, using negative exponent rule, we bring the negative 1/2 to the denominator, so we get 1/2 square root of x. So the derivative of first, that's 1/2 root x sine x, plus first times derivative of the second. Derivative of sine is cos x. And there you have it. Again, we're done. There's not much, again, we can't simplify this expression. And so we're going to leave it like this. Now later on, the expressions we will simplify, in fact, in all of these, starting the one I'm working with. It's just this particular one I couldn't simplify it. In number 16, we have y is equal to cosine of 2x. Now, cosine 2x, different ways, by the way, you can do some of these trig equations, that is, find the derivative of them. And that's partly because of trig identities. So now one thing, just you got to be careful, because we said the derivative of cosine x is sine x, right? Negative sine x, right? So if I say cosine 2x, derivative of that is just negative sine 2x. You're partially right with this, except it's not quite right. We have the correct initial step, but there's more in this. And the reason this isn't just negative sine 2x is because this is a composite function, what we're looking at. What makes it composite is that the argument of cosine is not just x, but it's 2x. So the argument of cosine itself is like a function of x. So for these, we'll look at them, in fact, in the next section, how we can actually do these directly without going through identities. But for now, let's see how this is going to be. Keep an eye on this answer. Okay, so we're going to see that answer, but not quite this, but a version of this one. So let's proceed. I'm going to write cosine as 1 minus 2 sine squared x. Right? Remember the cosine identity, the double angle identity. Cosine 2x is cosine squared x minus sine squared x. You can go this way, or that's 2 cosine squared x minus 1, or you can write it as 1 minus 2 sine squared x. There are 3 versions of the double angle identity for cosine. Now I chose the one that you're looking at with the sine in it. Now I'm going to take the derivative of this one. So this is now 1 minus 2. And you can think of sine squared x as sine x quantity squared. Those are the same. Now I can take the derivative. Derivative of 1 is 0. Negative 2, constant multiple. Here we're doing x to the n, which is n x to the n minus 1. So treat sine x as x. And n is 2. So this is going to be 2 sine x, right? 2 sine x. And the answer is going to be negative 4 sine x in this case. Or actually, hold on. I'm just writing it as what you call it, using double angle identity. Okay. And I'm not doing this formula yet. Okay, I jumped too soon. Now, that's just a function. Okay. Now, here's the next step. We can write sine x squared again, and the reason, because this also is a composite function. It's in the form of think of it as this. It's in the form of I don't know, w squared, where w is sine x. Okay, so if it was just w squared, we take the derivative of that to w. But then what about the fact that w itself is a function of something else? Again, this is a composition of functions, so that's why we got to hold off on how to find the derivative directly. So in this section, because we don't know about other methods, we're just going to write sine x squared as sine x times sine x. Okay. Here's f, here's g. We're going to do the product rule again with this function. So that's going to be 1 minus 2. Now, sine x times sine x, the product rule. You take the derivative of first. Derivative of sine is cosine times second plus first times derivative of second. Okay. And this is going to be, I took the derivative now, yes, so this is actually going to be 0. Derivative of a constant, that's going to be 0, okay? So we got just negative 2, and again, derivative of first by second plus first times derivative of second. So this is going to be negative 2. Now, inside brackets, we have, those are like terms, aren't they? So I have 2 sine x cos x. Now, remember, there is a double angle identity for that. That itself is an identity. So you really got to be sharp on your trig identities here. 2 sine x cosine x, that's going to be sine 2x, right? Sine of the double angle. So the answer, all said and done, is going to be negative 2 times sine 2x. Okay. Now compare this with that answer that we were going to do just off of derivative of cosine being negative sine. So you see similarities, almost correct, but there's a 2 in front. You see that? Which is an up here. This doesn't have it. So that's why we had to go through the process that we did, the way we did it. And there you go. That's number 16 for you. Now let's take a look at number 20. In number 20, we have 1 minus 10 divided by 1 plus cotan. Okay, let's take a look at number 20 now. In number 20, S is 1 minus 10t divided by 1 plus cotan t. Now, we're going to use the quotient rule, correct? Remember the quotient rule, I put it here on the side. F over g prime is, you square the denominator, repeat the denominator, derivative of the numerator minus numerator times derivative of denominator. It has to be in that form because in the numerator, subtraction is not commutative, so I can't swap it and write fg prime minus gf prime. That won't work. All right, let's proceed. Now this is going to end up being a long expression because it's the way you'll see it happens. So I'm getting ready for the long expression. So I'm going to square the denominator, 1 plus cotan t squared, and then repeat the denominator, that's 1 plus cotan t. And then derivative of numerator, derivative of a constant 1 is 0, negative, derivative of tangent is secant squared t. Okay, minus 1 minus tan t, that's numerator times derivative of the denominator. Derivative of, again, 1 is 0, and derivative of cotan is negative cosecant squared t. All the co-functions, the ones that start with co, the derivatives are negative. Okay, so that's something that helps you memorize or remember these, because we really do need to memorize derivative of trig functions. And I know probably, at home you have access to open resources, but going forward you really want to have these memorized. So remember, all the co-functions, that's cosine, cotangent, and cosecant. These, all the derivatives will be negative. Okay, now let's do this. Now, because we have a combination of tangent, cotangent, secant, cosecant, that's why it's going to be messy. Let's do a sideline here. So remember, secant is ratio of 1 over cosine, right? 1 over cosine t. And tangent is ratio of sine over cosine, right? Tan is sine t over cosine t. And of course, cotan is reciprocal of that. Cosecant is going to be 1 over sine. Because what we want to do is eventually we want to convert these to sine and cosine. Okay, and then maybe they can simplify that way a little easier. All right, so in fact, I'm going to do that. I'm going to convert all of these to their respective sine cosine form. So the first one, 1 plus cotan, that's cosine over sine. This is the busy work. Secant, 1 over cosine squared t, minus 1 minus sine over cosine t, and negative 1 over sine squared t. Okay, that's just the numerator. And the denominator is going to be 1 plus cosine t over sine t quantity squared. Okay, and I can align my equal sign. And there you have it. Now, at this point, because you can see it's kind of messy, right? Let's find the LCD and multiply top and the bottom by the LCD. Okay, now the LCD, that means look at just the denominators. Okay, I'm looking at only the denominators here. So what is the LCD of sine t? Sine t, cosine squared t, sine, that would be squared, sine squared t in the denominator, and cosine t sine squared t in the numerator. The the LCD of all of those end up being their product. Well, not their product quite, but the LCD actually going to be definitely sine squared t. That's from the denominator, this one, because it's squared. And that will cover this denominator, and of course, clearly sine t is in sine squared t. And then for cosine, I have cosine squared here. That's cosine squared t. Now, the advantage of multiplying top bottom by the LCD is that we can get rid of all complex denominators in just one step. Okay, so I'm going to multiply by LCD on top. Next step, all of a sudden, this is going to look a lot nicer because of the way we are handling this. Let me just put LCD in front. Okay, so keep in mind we're multiplying this by every expression in the numerator, there are two expressions in the numerator separated by minus sign. So I'm going to distribute LCD to, don't worry, I'm going to erase this line, to this. Okay, now, once you distribute the LCD, this denominator, right, the denominator is going to go away. Okay, so here's how it's going to work out. And this is the denominator I'm talking about. Okay, so let's do this. The first distribution is going to give me negative sine squared t, right? Because cosine squared t is going to cancel. 1 plus cosine t over sine t. Okay, that's the first part. And then minus the second distribution will actually get rid of sine squared t. Okay, so that's going to be minus cosine squared t. Actually, let's see, there's a minus in front of the fraction, minus here and a minus here. Those two negatives multiply to positive, so let me write plus here. Okay, plus, and that's just going to make it parentheses 1 minus sine t over cosine t times cosine squared t. Now in the next step, we're going to work this one even better. It's going to reduce even further. Okay, in the denominator, once you distribute the LCD, this is going to become, let's see, inside parentheses is going to be sine t plus cosine t, right? Square that. Right, I'm squaring. I'm combining these two, and so here's the numerator divided by sine squared t, and then squaring them at the same time, multiplied by LCD. When we do that, well, let me write the LCD now. LCD is, remember, sine squared t cosine squared t. So sine squared t is cross out, right? Okay. Now, let's distribute one more time in the numerator and now in the denominator. Let's see what's going to happen. Well, denominator isn't going to change much, right? Because I took out sine squared t. So my denominator is actually going to be stable now. It's going to be cosine squared t times sine t plus cosine t squared, right? Now in the numerator, I'm distributing sine squared and cosine squared to those fractions. So first I'm going to get negative sine squared t. Next distribution, we lose the sign in the denominator, so it's going to be negative sine t cosine t, and plus cosine squared t minus sine t cosine t. I'm running out of space. Let me move down here. So S prime is going to be, again, we have cosine squared t. So I knew this is going to be messy because we have a combination. We have 4 of the trig functions in there, and there's no identity to handle them. That's why. Negative sine t. So I knew it's going to be a bit messy. Plus cosine squared t. Okay, and then minus sine t cosine t. There you go. But then it's going to look better now, right? And here's why. Because so we have sine squared t. The sine squared t, I can write it as one negative sine squared t. I can write this as as just cosine squared t minus 1. Right? And that's using Pythagorean identity. Here's why. Sine squared t plus cosine squared t is 1, right? Pythagorean identity. So therefore sine squared t is 1 minus cosine squared t. Therefore negative of sine squared t, you just change the sign on those two. So it's going to be cosine squared t minus 1. That's the consequence of Pythagorean. And then sine t cosine t, we have negative 2 sine t cosine t. Those are like terms. Plus cosine squared t all over the denominator. We're pretty much done. As I said, the denominator has stabilized. So we're not going to change it there. And cosine squared t minus, cosine squared. Now this one and this one, those are like terms. So we can actually combine them into one. So this is going to be 2 cosine squared t negative sine. Remember 2 sine t cosine t, we can write that as sine of the double angle and then move the 1 to the last, to the end. This one, oops, gotta be careful with my pen. That was cosine t minus 1. There. That negative 1, I moved it to the end of the expression over the denominator. Cosine squared t sine t, and that's going to be sine t plus cosine t squared. Okay, and there you go. We're done with this one. All right, so again, this one, notice it took long. Notice there's no calculus in this after the first step. The only calculus part was right there, the top part. Everything else is algebra. Well, in this case, trig manipulation. Okay, so there we have this one, and that was, let me see, that was exercise number 20, the one we just looked at. Let's take a look at number 26. In number 26, we have a function of t. Again, we have a mix of algebraic and trig function, t squared plus 1 sine t. Number 26 question, find a second derivative. In number 26, we want to find the second derivative. Okay, so let's tackle this one. Exercise number 26, we have h of t was, let's see, was t squared plus 1 times sine t. Okay, so this is again going to be in the form of a product, f times g. Therefore, h prime of t is going to be, again, I'm going to take derivative of first by second plus first times derivative of second. Okay, so we just did f prime g plus f g prime. And then we want the second derivative, right? So let's do h double prime. H double prime t. Now, that's the derivative of the first derivative, the one that we just found. This constant multiple and then the product rule itself. Derivative of first by second plus first times derivative of second. So that's the derivative of the first expression. And then the last one is its own product rule. So we're going to go again, derivative of first times second and plus first times derivative of second. All right, so we're good with that one. Now let's tidy up that expression a bit. Let's see, I can factor a sine t. See, there's a sine here and sine here, right? And we can factor it. So once we factor sine t factored, we're going to get 2. And then because it's negative, distribute the negative to both of those. We get negative t squared minus 1, right? And then on cosine t, well, we have 2t cosine t, and 2 distributes to t cosine t gives me another 2t cosine t for a total of 4t cosine t. Okay. And then we're just about done with this. So that's going to be sine t. Oh, let me follow the structure. We usually, when we have a mixture of algebraic and trig, we put algebraic ones first. 2 minus 1 is 1, 1 minus t squared, and then followed by trig plus 4. That's just a convention. It's not like if I write it the other way around, is it wrong? No. It's just a convention. And there you have it. We're done with number 26. Number 26 is good. And one last one from this segment was, I believe, number 28, cosine theta over theta. Now that looks pretty innocent, right? We want, what, the second derivative of that one? Let's see how innocent it can remain. So for this one, I'm going to write number 28. We had w is equal cosine theta over theta. Very simple expression. Now again, notice though it's a mixture of trig and non-trig. So dw d theta, just to be different, you can go w prime. So it's going to be the denominator, you square it, repeat the denominator, derivative of cosine is negative sine theta, minus, and then the numerator times derivative of theta, which is 1. Remember, when you take the derivative of denominator, don't take that derivative of theta squared, the original denominator. Okay, so this is going to be, what? It's going to be negative cosine theta plus theta sine theta. I know why my pen is acting up again. Divided by theta squared. All right, now we need to take our second derivative. Now for the second derivative, let me again write it in a notation we haven't used before, so we get used to it. I'm going to move the negative, like a constant multiple, that's like negative 1, outside, just so we don't have to deal with that negative. So here's my negative moved to the front, and our fraction line. And you can see why the fraction line has to be this long, because the numerator is a combination of sum of two functions. The second term, the second function itself, is a product function. So when we take the derivative of the numerator, it's going to be a long expression. So let's begin. We squared the denominator, right? For now, I'm going to go here. Theta squared squared. We're done with the denominator. Repeat the denominator times derivative of the numerator. Derivative of cosine is negative sine theta. Okay. Plus. And then we take the derivative of theta sine theta. That itself, derivative of first by second plus first times derivative of second. Right? That's just derivative of the numerator. And then minus the numerator, which is cosine theta, plus theta sine theta, times derivative of the denominator, theta squared, which is 2 theta. So my fraction line was measured perfectly. Okay, now let's work this one. We have a couple of opposites. These two, sine theta, negative sine theta, they add to 0. That's good. They cross out. And then I'm going to distribute theta squared in the numerator. Here's a minus still. I'm going to distribute theta squared to the parentheses. I'm sorry, yeah, to theta cosine theta. So that's going to make it theta cubed cosine theta. And then negative 2 theta times cosine theta, 2 theta cosine theta, negative 2 theta squared sine theta, divided by theta fourth. Now, all expressions have theta in them, right? This one has 3, that one has 1, 4 down here, 2 up there. So 1 is common, right? One theta is common to all. I'm going to cross out one of the thetas, or you can factor it first and then cross it out. And then let's handle this negative. I'm going to distribute the negative to all three terms also as we go. So here goes. Remember, I'm going to take out the theta and distribute the sign. So this is going to be negative theta squared cosine theta plus 2. The theta is going to cross out, right? Oh, let's see. 2 theta times cosine theta is 2 theta cosine theta. Yeah, that looks good. Okay, and then let me write this one first. 2 theta squared sine theta. I'm trying to keep it in decreasing order of thetas. Plus, now put 2 theta cosine theta. All of that divided by, actually theta is gone, right? I'm working with this. Remember, I divided the theta out, so that's just 2 cosine theta divided by theta cubed. And there we have that one. So that's going to be the final answer for this. Let me get my theta right, and it's the final answer. And there you have it, all cleaned up. And that's it. That was exercise number 28. Okay. Now we're going to look at, and let me bring up more examples. We're going to take a look at another one in just a moment here. So let me pause and I'll be back. This exercise number 36, I have a graph of exercise number 36 right next to it that we can kind of see. We want to find the rate of change of the function with respect to x at indicated value of x, which is 0. Now from this graph, it looks like at 0, the tangent line, it looks to be horizontal, right? So let's see if the slope ends up being 0. But before we actually look at that, we need to find the derivative, and then I'm going to actually simplify the derivative as much as I can before actually plugging in a value of 0 in for it. Okay, so here we go. So I'm going to have this long fraction line. So it's the numerator times derivative of the numerator, which is the product of x tan x. So for that, I'm going to do derivative of first by second, plus first times derivative of tangent, which is secant squared x. Okay, and then we're going to subtract the numerator, x tan x, times derivative of secant, which is the denominator. That's going to be secant x tan x, all over square of the denominator. Okay, now in the numerator we have secant here and we have secant here in both of those expressions. So I'm going to factor secant out. That's going to make it secant x times tan x plus x secant squared x. Now the secant squared x identity, by the way, I'm looking inside the parentheses here. That secant squared x, I'm going to use the identity 1 plus tan squared x, okay, and replace it by that. So that's 1 plus tan squared x, okay, negative x tan x squared. Remember, secant, the secant here is factored out. Okay, and all of this divided by secant squared x. And then we can actually divide out a secant and a secant in the denominator. And all we end up with is the following. We have tan x plus x tan squared x minus x tan squared x, all of that divided by secant x. Okay, and now that's done. We have like terms. Those are like terms, are opposites, they add to 0. So we were able to actually reduce this a great deal, and that's kind of what we would like to do going forward. We want to reduce these expressions to as much as possible. Now we want to evaluate it at x equals 0. That's going to be the easy part now, right? At x equals 0, that's when you plug in 0 for these. So you go 0 plus tangent of 0 divided by secant of 0. Now, that's 0 plus 1, right? Because tangent of 0 is 1. So that's going to be 0 plus 1 divided by secant of 0 is also 1. I'm sorry, tangent of 0 is 0. I'm not sure what I was thinking of. So that's going to be 0 over 1, which is just 0. Okay, and we are good to go with this exercise. That's the answer. So it is indeed what the graph suggested. Okay, now let's take a look at exercise number 88. I'm going to bring that exercise up for you. All right, so this is actually exercise 38, not 88. It's number 38. In exercise number 38, and I have actually here drawn a graph of number 38. The function is x plus sine x. So the x part of it kind of gives you the line, that 45-degree angle line, and the sine x actually gives it that sine wave impression that's thrown on top of that. Okay. All right, and we want to know for at what values of x the slope of a tangent is equal to 1. Now, if you look at the graph, we have many points, like for example right there, here, 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 like that. You see that all of these have tangents 1. So there's going to be infinitely many of these, right, where the slope of a tangent is 1. So we want to find actually a whole class of them. So there you go. That's just one particular one. Okay, and I'm going to put m equals 1 at that point. We want to find these points. So let's find the derivative first in number 38. G prime of x is going to equal to, and let me, my pen is acting again. G prime x is equal to, derivative of x is 1, derivative of sine x is cosine x, right? And we want to know where that's equal 1, so we're going to set it actually equal to 1 and then try to work it. Now let's solve this equation. I'm going to subtract 1 from both sides and we get cos x is equal to 0. So the places where cosine is 0 means zeros of cosine, that's where the tangent line is 1. Now if you recall from the unit circle, cosine is 0 at 90 degrees, right, which is pi over 2. And it's also 0 at 3 pi over 2, right, which is 90 and 270 degrees. That's of course taken the direction in the counterclockwise direction. The angle could be negative also, so we need to consider that as well. I'm looking at counterclockwise rotation here. So here's 1, 0, and then you go on forward. Here's another, the value of the angle where the derivative is 0, and then you continue, successive rotations around the circle is going to make cosine 0. So that's again taking it in a counterclockwise direction. In a clockwise direction, let's see, there's my circle. Again, my pen is having trouble here. Let me see, in a clockwise direction, sorry about this. Anyway, the same circle. I'm going in this direction now, in this direction, and the same thing happens this time. Negative angle, if I look at this as negative pi over 2, and then this would be negative 3 pi over 2. Okay, let me pause this. Okay, let me now go in a clockwise direction. In a clockwise direction, in that direction, I come across negative pi over 2 and then negative 3 pi over 2, like that. Okay, so anyway, the zeros of cosine. The zeros are when x is pi over 2, and then every 90 degrees, right? Or actually every 180 degrees from top to bottom is 180 degrees. Every k pi will pick up another 0 here. K is an integer. So k's, that's z, this notation, funny looking z means integers. Okay, so k must be integers. And because it's an integer, it picks up both clockwise and counterclockwise moves around the units, around the circle. Okay, and with that, we are done with this section.